The speed through any medium, meters per second, stays the same. But as frequency increases, the wavelength decreases. One can create very small waves with a small wavelength on the matter of centimetres and a period of 0.1 second to 5 or 6 seconds. Strong winds can have a wavelength of 10 to 20 metres and maybe a period of time of 20 seconds. And then tsunamis created by earthquakes or severe storms may be 1,000 seconds and thousands of metres. And then, of course, tides, which might have a time period between crests of hours, 12 hours, 13 hours, will be massively long, thousands of kilometres. But no matter what the frequency or wavelength, they all have certain characteristics in common.
Kia ora, Steve here again, and welcome to the third topic, light. How do we know that light behaves like waves? Because it does wave stuff. So now in the house you can investigate for yourself the wave nature of waves. Just need a roasting dish, a chopping board. The chopping board is there to make the waves. Some water, put the water in the dish, and then make your waves. It's good to be under a light, a bright light. You can see the waves a lot easier. If you want to, photograph them in slow motion and look at it back. You don't have to. And then you've got your blocks and pieces, reflection, obstacles, making gaps or islands, and investigate the nature of the wave as it moves and as it happens, and then we can refer to the light later on in the same context.
Referring back to our particle model of nature, we'll see that as the energy of the wave disturbs and is picked up by the particles here, the H2O, the CO2, the O2, the hydroxide ions, the hydrogen ions, the chloride and sodium ions, we'll see that they gain more energy, they move around a lot more, take up more space, and this is the heat. This is increasing heat and reaction time. Once the source of energy has generated the wave continues to move. Even if that source of energy is removed or it stops, the wave continues to move. Waves bounce off surfaces. This is called reflection. Diffraction is where the wave bends around corners. If it goes around an object that is greater than a wavelength wide, then it tends to bend. You can see how a landmass would change the nature of a wavefront and how this could be used in navigation at sea, as it was by the Polynesians, by picking up changes of wave pattern downwave from an island. If the wave travels through a gap smaller than the wavelength, then it forms a circular wavefront once it's gone through that gap. Interference is overlap of wave frequency and wavelength. It's easiest to see in a two-slit interference pattern where the diffraction as the wave moves through two slits and forms two circular patterns, or diffraction around an object forming two diffracted fronts overlap, and where two crests will reinforce each other and crests and troughs will cancel out. Refraction is what happens when waves move from one medium to another. For the case of our ocean wave, that is from a deep water area to a shallow water area, and this affects the speed. So as it slows down as it enters the shallow water, the wave front comes behind the original wave and it is bent. Light shows all these characteristics of waves, and in GTV 3.2 we'll look at refraction in more detail.